even though y'all still have some practicing on the chain rule and differentiation, we have to move on. And the next section is implicit differentiation. And I want to show you two things in the book, and then we'll do some examples. Number one, you have to figure out when you can differentiate explicitly and when what we've done so far doesn't work. If you have the y completely by itself, if you have a function of y in terms of x, then you don't need implicit differentiation. This one you could just use the power rule and you'd get that derivative as 6x. So if you have y in terms of x, then you don't need implicit differentiation. You only need implicit differentiation when it's hard to get the y by itself. Now, this particular problem, that is the implicit form of that equation because the y is not by itself, but it would be easy to get the y by itself. All you'd have to do is divide both sides by x, and if you did divide both sides by x, then you could differentiate explicitly. On other problems where it's hard to get the y by itself, that's when you're going to use implicit differentiation. For example, right here. Example 2 in the book. It would be hard to solve that equation for y. You might be able to, but it would be a pain in the rear. So instead of solving that for y, I'm going to use implicit differentiation. And the implicit differentiation is basically just a version of the chain rule. Tell me what the derivative of ugly squared is. Just 2 ugly, all right? Ugly is some function of x, and I really know what it is. Here, y is some function of x, and I don't know what it is. I know that somebody could get the y by itself, and that y is some function of x. I just don't know how to get it by itself. So I'm going to treat that y cubed as ugly cubed. What's the derivative of ugly cubed?
3
ugly squared times what?
Derivative of the ugly.
Derivative of the ugly. Now the derivative of y, I don't know anything else to call it other than either dy over dx or just y prime. That's 2 symbols for the derivative of y. The book uses dy over dx. I'm going to use y prime just because it's easier to write. But right here is my derivative of y cubed is 3y squared times the derivative of the y. It's just like 3y squared derivative of the ugly. The derivative of y squared is 2y times the derivative of y. The derivative of negative 5y is just negative 5 times the derivative of y. And then the derivative of x squared is just 2x. I don't have to have the derivative with respect to x because x is the variable we're differentiating with respect to. We're finding the derivative with respect to x. So it's only when, let me show you one other thing, it's only when your variables don't agree. When you're differentiating a y with respect to x, you're going to have a y prime. If you were differentiating an ugly with respect to x, you'd have to have an ugly prime. Now, here's some good steps to go by, and then we're ready to do our examples. To differentiate implicitly, you take the derivative of both sides with respect to x, and that means any term with a y in it is going to have a y prime as part of that term. Then you just solve for y prime. To solve for y prime, just a second. To solve for y prime, you get all your terms with a y prime on one side, all the terms without a y prime on the other. factor out a y prime if you need to, and then divide both sides by whatever's left after you factored out the y prime. These last three steps are just algebra. The only calculus here is that first step, and remembering whenever you differentiate a term with a y in it, that term is going to have a y prime. Now, Harriman, what did you want to ask?
You had just lost me, but I got it now.
And most things don't make sense till you see an example. So let's do one example, and if you still have a question after that, I'll try to explain it better. But these steps don't make a whole lot of sense until you've seen one example. So here's your one. Oh, here's the page I was looking for. Let me show you this. This is example 3. Part A wouldn't take implicit differentiating because you're differentiating something with an x in it with respect to x. Your variables agree, you don't have to use implicit differentiation. But in the B part, you're taking the derivative of y with respect to x. That's when you have to use implicit differentiation. The derivative with respect to x of y cubed would be 3y squared, but you're also going to have a y prime because y is some ugly that you don't know exactly what it is. Think of that as ugly cubed. The derivative of ugly cubed is 3 ugly squared times the derivative of the ugly.
So we'd just be taking the derivative of y, which would just be 1. Is that what you're saying?
No. We can't take the derivative of y because we don't know exactly what y is. Y is some ugly. This is like your ugly prime, only you don't know what the ugly is. I know. Let's do an example. I promise that'll make it better. From page 171. Number 4. This one's going to make it all better. Just like in everything we've done so far in chapter 3, we're trying to find the derivative of y with respect to x. Our left-hand side, when we find the derivative, there are several different ways to write that derivative. F prime of x is one way to write the derivative. Y prime is one way to write the derivative. Dy over dx. All three of those are just 3 different ways of writing the derivative. This one won't make sense in this section because we don't have f of x. We don't have the y by itself. So we're either going to use y prime or dy over dx for the derivative. All right, in this first term, what's the derivative of x cubed?
3x squared.
3x squared. And I don't have to have the derivative of x because the derivative of x is just 1. If I'm differentiating with respect to x. But the second term is not just x cubed, it's ugly cubed or y cubed. The derivative of y cubed is what? 3y squared, but also times y prime. This is like the derivative of ugly cubed is 3 ugly squared times the derivative of the ugly. All I can do is just write y prime because I don't know what y is exactly.
Okay, so the thing about that is the first one you did the same way as that, just the derivative of x is just 1.
Correct. So anytime you're differentiating a term with an x in it, it's just like 3-1 to 3-4.
Okay.
But when you differentiate a term with a y in it, you're going to have a y prime. So I'm going to write you a note out here since I didn't type up any notes for this section. The derivative to x, and we're always differentiating with respect to x, we just usually don't say that. The derivative with respect to x of any term with a y in it will contain a y prime as a factor. Anytime you take the derivative of a term with respect to x of a term that has a y in it, that term of the derivative is going to have a y prime in it. Because y is some ugly, you don't know exactly what it is. Now this problem, we could have solved that for y. We could have subtracted x cubed from both sides, and we could have taken the cube root of both sides, and we could have gotten the y by itself. Maybe if I did this problem that way, you would embrace implicit differentiation more quickly, because this is less ugly than differentiating y equals cube root of 64 minus x cubed. This implicit. I'm sorry, what?
Can I see the little asterisk you wrote for a second?
Yes, yes.
What's with respect to x mean on that?
Again, when, let's say a problem that we had been doing in section 3.2, we wanted to find the derivative of x squared.
Yeah, that's okay.
If you look back in your notes, you may not have known why I was doing it at the time, but I wrote the derivative of 3x squared with respect to x. You remember me writing it this way?
Yeah.
On most problems, I didn't say with respect to x, but it's understood that all the derivatives we've been taking so far, x has been our dependent variable. We've been taking the derivative with respect to the dependent variable, and that's why we haven't had to use implicit differentiation. If I was taking the derivative with respect to x of 3y squared, then that's going to take implicit differentiation.
Okay, I'm following that now.
Okie dokie.
I see the rest of that asterisk, please.
Yes. No, that's okay. That's why I type up notes for most sections. Doggone it, I don't know what's wrong with my voice. I type up notes for most sections so that we don't have to spend time copying stuff down, but really this is the only note I need to write in this section.
Now that problem wasn't done, right?
No. We had to discuss why we had to have a y prime in the second term, but now we're going to finish. Now, what's the derivative of 64? 0. For some reason, my most common mistake, personally, is bringing down the 64 instead of taking the derivative of the 64. Make sure you don't do that. You're taking the derivative of each term, and the derivative of 64 is 0. Now, just like all the differentiation we've done so far, we want our answer to end up with the y prime by itself. So from here on out, it's just algebra. How do you get that y prime by itself? First, you would subtract the 3x squared. And then what?
3y squared.
Divide by 3y squared. And your 3's would cancel and just leave you negative x squared over y squared. These derivatives, in comparison to all the derivatives we've done before, They're different because the derivative may end up with both x's and y's in it. All of the derivatives we did on test 2 just had y prime equals, and then the right-hand side just had x's in it. Now this one is finished because the direction said find the derivative. Well, that's what y prime is. Y prime's the derivative. Now, that's the very simplest example we can do. And, of course, they're going to get uglier, but the concept is going to remain the same on every problem. We're going to take the derivative of both sides with respect to x, and then we're going to solve for y prime. It's the solving for y prime that gets ugly sometimes.
Is it
Yes,
always
ma'am.
going to be respect to x, not
Yes.
respect to y?
Correct.
Okay.
Always going to be with respect to x. Until you get to calculus 2. But I don't have to discuss that. Number 6. You could possibly solve that for y. It's quite possible that if you did, the expression that you would end up with would be uglier to differentiate than just using implicit differentiation. So I'm just going to use implicit. I'm not going to solve for y unless the book tells me I have to. All right. Just look at that first term. What do you think it's going to take? Which one of our rules are we going to have to use to take the derivative of x squared y? It's going to take the product rule because this is a product. Same thing with the second term. You got to recognize that as a product, and if putting a dot in there helps you recognize it as a product, then do that. All right? We're going to start with this first term, the first factor times the derivative of the second. Well, here's the first factor. What's the derivative of the second? Derivative of y is just 1 y prime. I don't have to write the 1, just y prime.
Wait, why is it 1 and 1
Just like if you took the derivative of x with respect to x, it's 1. If you take the derivative of y with respect to x, it's 1, but also y prime.
So why didn't we take the derivative of x squared right there?
The product rule says the first factor times the derivative of the second plus what?
Oh, okay.
The second times the derivative of the first is 2x. The reason I skipped a line on my paper was so that I could say both of those terms are the derivative of that first term by the product rule. Now I'm also going to have to use the product rule on this second term. So bring down the plus. Product rule starts the first factor times the derivative of the second. What's the derivative of just x? 1. Do you have to write that 1? No. Y squared times 1 is just y squared. That's the first factor times the derivative of the second. Now I need to add the second factor times, what's the derivative of the first? 2y times y prime. Doesn't matter in what order you wrote those. I wrote them wherever I had room. That's the second factor times the derivative of the first. These two terms come from that. And on the right-hand side, what is the derivative of -3? 0. Any questions about that step?
Yeah,
Okay, tell me.
you lost me after y squared.
I think because the way I wrote it here, what if instead of writing it in that order, I had written x times 2y, y prime? that might have made more sense to you because that is the second factor. Look right here, Sarah. Here's the second factor. The derivative of y squared is 2y times y prime. Okay. Now I'm solving for y prime, so what do I do next?
So it's equal to 0.
Okay, well, I didn't set it equal to 0. It already is set equal to 0 because the derivative of -3 is 0.
Did you factor out a y?
I need to do one thing before I factor out a y because two of these terms have y primes and two of them don't have y primes.
Do you separate them?
How?
Like put the y primes together, put the y's together.
Get all the terms with a y prime on one side and all the terms without a y prime on the other. I could have written this 2xy y prime just as it was written on the step above, but instead of x times 2y, I decided to write it 2xy. Then what? Now you can factor out a y prime. Yes, it's kind of hard to see my prime there. Let me make it bigger. Then divide by the stuff that was left after you factored out a y prime. That's the derivative. And it's ugly. It has both x's and y's in it. But we have done what we set out to do. We found the derivative of y. We have the y prime by itself. The hardest part of this problem, or the most common reason for missing this problem, is failure to realize this is going to take the product rule and that's going to take the product rule. So I'm going to get two terms for the derivative of the first term and two terms for the derivative of the second term. Any questions on that one?
You treat the y like an ugly.
You treat the y's are an ugly. Yeah, the y's are an ugly. This is ugly prime. All right. Let's go to number 8. This first term isn't just e to the x. If it was just e to the x, the derivative would be what? E to the x. But this is not just e to the x, it's e to some ugly, where the ugly has a y in it. So when I take the derivative of e to the xy, I'm not only going to get e to the same old xy, I'm also going to have to do what?
Derivative of the ugly.
Derivative of the xy, and what is it going to take to differentiate the exponent there? That's going to take the product rule. But you got there, so you realize that exponent's a product, and when you differentiate it, you're going to get two terms. The derivative of xy is x times the derivative of y plus y times the derivative of x. And what is the derivative of x? 1. You don't even have to write it, but I did so that you could see this is just the product rule applied to x times y. First derivative of the second plus the second derivative of the first. Are we through differentiating the first term? Yes. The derivative of e to the ugly is e to the same old ugly, and this is the derivative of the ugly. So move on to the next term. What's the derivative of x squared?
2x.
2x. Is that all? Yeah, you could say derivative of x is 1, but you don't have to write it. What about the derivative of negative y squared?
Negative 2y times y prime.
Yep. And what's the derivative of 10? 0. We're through with calculus. Now we need to do the algebra of solving for y prime. Talk to me. How am I going to be able to get...
Move the 2x over.
Would you move the 2y prime over? Nope. Okay.
That would be legal. I'm not sure it would be helpful because then I'd have y primes on the left and y primes on the right. You're going to have to distribute that e to the xy so that you can get the terms with a y prime on one side and the terms without a y prime on the other. Just as if that were a 3. You'd have to distribute the 3. Here we have to distribute e to the xy. X, e to the xy, y prime, plus y e to the xy. And that's all I'm going to do in that step. Now, yes.
You distributed e to the raised to the x times y.
That's exactly right.
So could you have wrote that as a e to the x times y prime?
E to the x. Say that one more time.
E raised to the x times y and multiply that by y and then by y prime. Could you just write it in that order instead of writing it like that?
Let me come out here to the side because I'm having difficulty hearing the parentheses in your voice. Do you realize that your voice had parentheses? This would be the same thing.
Yeah, that's what I'm saying. All right.
Yeah. I thought you were throwing an extra y in there. But as long as you weren't, then these two things are the same. All right, now I have 4 terms. 2 of them have a y prime, 2 don't have a y prime. What do I need to do?
The y primes.
Terms with a y prime on one side, terms without a y prime on the other. Then what? Factor out a y prime. And then what?
Divide that. X e with xy.
Divide by the stuff left in parentheses. If you have that on your paper and then you look in the back of the book and they have this. Are those the same?
Yeah.
Yes.
Wait, actually, no, because I left the, sorry, I left the E out of the denominator. Now are they the same?
Yes.
Yes. Which one looks simpler, my answer or the answer in the back?
The answer in the back.
The answer in the back has less negatives in it, and in general, the less negatives you have, the better. I'd count either one right on the test, but I want you to see that if you come up with this answer, all you have to do is factor a -1 out of the numerator and put it in the denominator, and then you have an expression that, yeah, it does look a little simpler. Now, what I've tried to model for you for the past 8 weeks, yes, it's my job to teach you concepts, but it's also my job to model good mathematical behavior. All right? So what I've tried to do on every problem is write neatly, work down the page, make sure every line is equivalent to the line above it before I continue. All the way down the page, I have a left-hand side and a right-hand side of my equation. Left-hand side, right-hand side, left-hand side, right-hand side, and boom, there's my answer. I think that possibly Einstein was so genius that his work wouldn't have looked that neat, and he still would have gotten the right answer. If you're Einstein, you can make work that doesn't look that neat and still get the right answer. But if you're not Einstein and you didn't do well on that test, maybe it's time to stop chicken scratching and model good mathematical behavior. Write neatly, make sure that every line's equivalent to the line above it. Those things that on the test you say, oh, I just made a little mistake. I'm tempted to say you didn't stop and make sure that line was equivalent to the line above it before you continued, so you didn't find your mistake. If you don't find your mistake, I'm going to find your mistake, and it's going to hurt worse than if you had found it. Another common mistake that causes calculus grades to be lower sometimes is the impulse to say, well, I didn't get the answer in the back of the book, but I understand what they did, therefore I'm okay. Yes, you're okay on that problem, but if I give you a similar problem, you're going to make the same mistake unless you practice until you can work and get the right answer without having to look in the back of the book. That's when you're okay. All right, I have, let's see. Here's one that's a little more difficult. Oops, sorry.
That's not good.
Well, we gotta take the derivative of that whole thing and the ugly part of it.
Yep. This is some huge, ugly squared. And what is the derivative of some huge, ugly squared?
2 ugly times the derivative of the ugly.
Man, you said it just like a math teacher. 2 times the same old ugly to the first. And of course, you don't have to write that 1. But I'm trying to get you to see that this is just 2 ugly to the first. And now I'm going to have the derivative of the ugly. I know the right-hand side is going to be 0. What about the derivative of the ugly? What's the derivative of sine pi x?
Cosine pi x.
Cosine pi x, but there's more.
Alright.
Times pi. You have to have the derivative of the argument there. Derivative of sine ugly is cosine, same old ugly, times the derivative of the ugly. What about cosine pi y? What's the derivative of cosine ugly? Negative sine, same old ugly, and then what?
Not the derivative of
The derivative of pi y is what? Pi. Ooh, very good. Pi y prime. Where in the world do I have room to write that? Pi y prime. Let me zoom in on just that second factor. Make sure you see it. It's written terribly here. Pi cosine pi x minus pi y prime sine pi y.
Okay, y prime again.
Because if I just said in a previous example, what is the derivative of pi y with respect to x? Play like it's 3y. What's the derivative of 3y with respect to x? Just 3, but also y prime. It would be 3y prime. Here it's pi y prime. You just can't see my little minus because my minus and my pi ran together right there. All right, that was terrible. But it's this next step that every time I do this problem, I have to think about why this next step is legal. In the back of the book, when I look at this in the solutions manual, the next step is this.
Oh. Yes, that's where sine and cosine.
No. How in the world can they put, actually it would be this, and that kind of gives it away. How in the world can they put plus or minus square root of 2 in place of that whole factor? I did it again this morning and I had to sit down and think about it. Where did the square root of 2 come from?
Did they set them both
They use the unit circle.
No, you can't just use the unit circle because you don't know what x and y are. Fine. I mean, you could find. I don't know what x and y are, so I don't know what to look at on the unit circle.
What's sine pi and cosine pi?
Oh, it's so sneaky. What do you get if you take the square root of both sides of the original equation?
Oh.
Ooh,
Plus cosine squared.
you just get ugly equals plus or minus square root of 2. This is the same ugly. I'm going to write you a note right here that says,
Oh, is it the same as?
take the square root.
Would you count half off if we didn't do that on the test? If we didn't?
Let me show you why it's going to make it much easier. Just hang on to that question just a minute. Take the square root of both sides of the original equation. And when you do, you'll get sine of pi x plus cosine of pi y equals plus or minus square root of 2. Let me let you copy down that part, and then I'll slide it over so that you can copy down the rest. Anyone still writing that part? All right, here's the second part, and then I'll explain it. All right. Just tell me this as a comparison to something that's easier. If I had something easier, negative, let's say, not negative, just square root of 2 times x plus 2 times x minus 3 equals 0. I'm just making up an easier problem. When I have something in factored form and set equal to 0, my next step is set each factor equal to 0, right? But when you set square root of 2 equal to 0, does that give you a solution? No. You only get two solutions here, negative 2 and positive 3. You can either think square root of 2 equals 0 doesn't give you a solution, or you can think divide both sides by square root of 2 and then that's gone. Either way you think of that's okay. But you understand why you don't have to set this equal to 0. For the same reason, realizing that this horrible thing is just plus or minus 2 square root of 2 makes the problem much easier to solve because I don't have to set this factor equal to 0. It's a constant. Now, anything that happens frequently in calculus, I've been doing it so long I just have it memorized. This is one of those infrequent things that you have to think about. Why? Those weirdo things usually don't show up on the test. They never show up on the test in more than one problem. But this is just one of those weird things that realizing, hey, that's just a constant, saves you a lot of work because now we only have to set this factor equal to 0.
So what you did is you, at the beginning, took the square root of both sides and found out what that was equal to, and then you just substituted into the problem?
Yes, I didn't do that as my second step because I didn't realize that was going to be necessary. I did the calculus first. I took the derivative of both sides. But then I realized, hey, this is just square root of 2. Actually, plus or minus square root of 2. And therefore, I don't have to set this equal to 0. I only have to set that equal to 0.
So when you have sine of pi times x plus cosine of pi times y equals plus or minus the square root of 2, how does that get to 2 square root of 2?
Then I did substitute plus or minus square root of 2 in place of that factor. I put plus or minus square root of 2 in place of that whole thing, and then my leading coefficient became plus or minus 2 square root of 2 because I put square root of 2 in place of this whole factor.
I still don't even know what you're taking the square root of and where you're getting the square root of 2. Like, I just...
Okay, cover this up for a second. Sarah, if I just said take the square root of both sides of that equation, and you don't really have to know why, I just want to see if you can, what would you have when you took the square root of both sides? What's the square root of ugly squared?
Ugly?
Plus or minus, because whenever you take the square root of both sides, you always pick up that plus or minus. Mm-hmm. So I would just have ugly equals, what would I have on the right-hand side? Plus or minus square root of 2. I didn't know in advance that that thought was even going to be necessary. I didn't think, oh, let's take the square root of both sides when I saw the original problem. When I saw the original problem, I said, that's ugly squared equals 2. The derivative of ugly squared is 2 ugly to the first times the derivative of the ugly. And then I thought, hey, but this guy, I can just put a plus or minus square root of 2 in its place. Because actually, that's what it equals.
I don't understand it unless we do the problem over again and approach it from
I don't think there's any way you could have anticipated the need to take the square root of both sides in the beginning. Nothing in my brain goes, ooh, let's take the square root of both sides. I don't realize that's going to be necessary until after I've taken the derivative. Honestly, and I'm just being totally honest with you here, I wouldn't have thought, oh, put a square root of 2 in place of that, unless I looked at the solutions manual and saw, oh, that's what they did. And yes, it makes sense. That's why I'm saying it's one of those rare, weird things that happens every once in a while, very rarely, not going to happen on the test. But I do want you to be able to look at it and say, okay, I see what they did. They said this whole thing right here is just plus or minus square root of 2.
So how is it?
Let me do this for you, Sarah. If I have, look at this. If I had ugly squared equals 2, then what's ugly?
Easier.
You would, if I had x squared equals 2, then what would x be?
What would X be?
Mm-hmm. If you solved that for x. Okay, so if that is ugly squared equals 2, and I take the derivative of both sides, what's the derivative of ugly squared?
Ugly times 2.
2 ugly times the derivative of the ugly. And what can I put in place of this ugly? Going back to the original equation, what does ugly equal? Just
Plus or minus the root.
yeah, just like you solve that for x, you could solve that for ugly. You could take the square root of both sides and get ugly is plus or minus square root of 2. That's all we did right here. We took the square root of both sides and said, well, let's just put square root of 2 in place of the ugly.
Okay.
All right. We need to move on. I don't want to spend 30 minutes on one problem. But if you still don't get it and you come talk to me or send me an email or something, I'll try to explain it better. I do want to write you one other note about what I'm fixing to do. After this line, I'm going to say then divide both sides by plus or minus 2 square root of 2. I just don't want you to think that in my next line, 2 square root of 2 disappeared. Nothing in math disappears. But if you divide both sides by the coefficient, 0 divided by that is still 0. And you only have the second factor to contend with now.
Would you get y prime by itself?
Yes, that's the goal in all of these problems.
So we just
Get
got
the
rid
box.
of the 2 square root of 2s.
But not hocus pocus. How did we get rid of it?
Does it equal to 0, 0? Or just, it don't
Or-
matter.
Yes, it doesn't equal 0 no matter what x is. You can either think it's no point in setting a constant equal to 0, or you can think divide both sides by the constant. Either way, all you're left with is the second factor equals 0. And then to solve for y prime, just to get the least possible number of negatives, I'm going to add pi y prime sine pi y to both sides, instead of subtracting the other and having two negatives, just adding the term with the y prime to both sides and dividing by the stuff that's with it. What do I need to divide by? Pi sine pi y, because you need that you need the y prime by itself, so you have to divide by what's with it. I'm going to turn the whole thing around. Lost a pi. And then what? You don't have to factor it out because it's already a factor, but you can just cancel it.
Cancel the pies.
Just like you would cancel 2 3s. If you had 3x over 3y, wouldn't you cancel the 3s?
I have a question.
Hold on 1 second. My person that said, is it okay to cancel the pies? Would it be okay to cancel 3s? If you had 3 times x over 3 times y?
Yeah, I guess if you factor out. Yeah, you ain't got to factor it out, so yeah.
No, exactly. No, you don't have to factor it out because the 3s would already be factors. If that was 3 plus x and 3 plus y, you couldn't touch it. But if it's 3 times x and 3 times y, you can cancel the 3s, and for the same reason, you can cancel the pi's there. Now, what did my other person ask?
Because it's cosine pi and then like sine pi, is there any way that can go to a cotangent?
Cotangent.
I would love for that to simplify to cotangent, but that would only work if the arguments were the same. And the arguments aren't the same. One of them has an x and one of them has a y. So no, that's not cotangent of anything because their arguments are different.
So we're finished?
Okay.
All right, so y prime equals cosine pi x divided by sine pi y. And at this point in the semester, I feel like I'm speaking Chinese. That pi y prime sine pi y, how Asian did that sound?
It's actually a pi day, right?
I love Pi Day so much. I had my first child on Pi Day.
314.
My first baby was born on Pi Day. The second baby was born on Valentine's Day. That kind of gives you a hint of my priorities. Math, love. I got it. Let me just tell you this. I got an email on Pi Day. Pi Day was Friday. I know because it's my oldest child's birthday. I got an email that said March 14th of next year
Okay, so 1415.
at, let's see, March 14th next year at something like 9:23 and 50-something seconds is going to be the most magical day of all because pi is 3.1415923 something. And so at my house, there are fireworks going off. 3:14, 15, 9:23, some number of seconds. Yeah, that's pretty darn cool. It'll never happen
We'll be
again.
taking shots on that day.
Huh?
Nothing.
Oh, okay. See, I won't know y'all by then. Y'all will be all gone and not writing me and all that stuff.
What's your
Okay. Gosh, how are we doing? Is that, let me think.
It's almost 12:10.
Oh no, that's bad. We only have 10-15 minutes. Oh, that's really, really bad. Let me skip over. I'm going to change the homework a little bit, but let me tell you one thing about number 2. Unfortunately, I'm not going to have, or 32. Unfortunately, I don't have time to write it because I do need to show you something else in our last 15 minutes. And then I'll tell you what the new homework is. Number 32 said, find the slope of the tangent line to this curve at the point 2, 3. How have I always found the slope of the tangent line?
Get the derivative.
Find the derivative and then,
Point slope.
well, that's the equation of the tangent line. If the direction said the equation of the tangent line, I'd have to use point slope form. But if it just says find the slope, so far we've only had to substitute the x because our derivative only had x's in it. Here, believe me, there's a lot of work in getting to this point. That's why I don't want to do this problem. But here, I ended up with the derivative being this. The slope of the tangent line, you have to substitute 2 in the place of x, 3 in place of the y, and get the slope of the tangent line is 2/5. So it's the same thing, only you have to substitute an x and a y instead of just the x. Now, if we'd had another whole day, we'd look at the graph of some of these bizarre things. They have names. This is called, this graph of this equation is called a bifolium. Yeah, or bunny ears, whichever makes you happiest, whichever one makes you sound smartest. This is called the folium of Descartes. This is called the Witch of Agnesy. I don't know why, but these really weird looking functions very often are something special known by people who are smarter than me. And that's not a large percentage of the population, but a small percent of the population. Okay. So, you know how to do the problems. I know that you could use more examples, and I wish that I could give them to you, but you have the basic idea of how to do implicit differentiation, and you know how to find the slope of the tangent line once you have that derivative. So the other thing that I have 10 minutes to show you, yes ma'am?
I'll go ahead, I'll ask you.
Okay. The other thing that I have 10 minutes to show you is called logarithmic differentiation. I need my Harriman folks not to be talking at all because I have to do this quickly.
Okay.
All right. Number 72, same section. That does have the y by itself, so I could take the derivative as is. I'd have to call that some huge ugly to the 1/2, and then when I went to take the derivative of the ugly, I'd have to use the 3-factor product rule. It would be horrible. I could do it, but it'd be horrible. All right? So instead of trying this as y equals ugly to the 1/2, there's a little neat trick that you can use when something would be too ugly to differentiate by the chain rule. Remember the problems that we differentiated log of, say, x squared over x plus 1 times x plus 2? We said that will be easier to differentiate if we separate it into the sum or the difference of logs. Well, here, we don't have any logs that would allow us to do that. But we could, if we wanted to, take the log of both sides. Now, let me go ahead and do that. Take the log of both sides, because that's an illegal thing to do. And on the right-hand side, I'm going to write that as x squared times x plus 1 times x plus 2 to the 1/2. I just rewrote the radical as an exponent. But that is certainly a legal thing to do. And for a second, I don't know how that's made life any better. Most times, throwing a log in there makes life worse. But what that allows me to do is, I'm not doing calculus yet, I'm just applying my rules of algebra that tell me I can bring the 1/2 out in front of the natural log and then split this log of 3 factors into the sum of 3 logs. Again, that's not calculus. That's my properties of logarithms that say if I have a log of something to a constant, I can bring the constant out front and write the log of a product as the sum of logs. Be careful to use your brackets carefully there. Here comes the calculus. What's the derivative on the left-hand side? What's the derivative of natural log of y with respect to x? No. Oh, yes, I heard somebody in Harriman. The derivative of natural log of ugly is 1 over ugly times the derivative of the ugly. All right. On the right-hand side, I have a constant times a big function. I'm just going to keep up with the constant and take the derivative of the function. What's the derivative of 2 natural log of x? I say 2 times 1 over x.
2 times 1 over
Yes.
x.
Better known as just 2 over x. That's the same thing. What's the derivative of natural log of x plus 1?
1 over x plus
1 over x plus 1. What's the derivative of natural log of x plus 2?
1 over x plus 2.
1 over x plus 2. What are we solving for? Y prime. What would we have to do to have the y prime by itself? Multiply both sides by y. And just because we're in a bit of a hurry here, and I did this problem a little bit earlier today, if I can find, oh no, I thought I had that derivative written down nicely somewhere. I do. Ah, here it is. After I got a common denominator and combined like terms, which took me about 3 more steps, I had 4x squared plus 9x plus 4.
And that's the final answer.
Nope, that's not the final answer. All right. Now, I did leave out some important steps there, but you're supposed to know how to add fractions, so I feel like I'm not being a bad person by skipping those steps. There are 2 more steps. This y is actually explicitly defined in terms of x. In place of that y, I could put all this stuff and have a derivative that only had x's in it. In the place of y, I'm going to, instead of putting all that stuff under a radical, I'm going to say square root of x squared is just x. And then square root of x plus 1 is x plus 1 to the 1/2. And square root of x plus 2 is x plus 2 to the 1/2. And then that derivative did was put what y was defined to be in the original equation in the place of y so that I had a derivative with only x's in it. And then because this is all over 1, I can cross-cancel my common factors.
Where did the 1/2? Oh, okay. I got
Yeah,
it.
it's right there. All right, so in my numerator, all I'm going to have left is the 4x squared plus 9x plus 4. In the denominator, I'm going to have the 2 from the 1/2. When I cross-cancel common factors, what happens to these x's? X divided by x is 1. What about when I divide the x plus 1s? X plus 1 to the 1/2 divided by x plus 1 to the first. What do I do with the exponents? Subtract, and 1/2 minus 1 is negative 1/2. Or I just have x plus 1 to the positive 1/2 left in the denominator. And the same thing with the x plus 2's. When I subtract their exponents, I get x plus 2 to the negative 1/2. That's x plus 2 to the positive 1/2 when I put it in the denominator. In the back of the book, they put that back under a radical, 2 times the square root of x plus 1 times x plus 2. I don't care if you do that or not. Now, I most certainly do not think that one example of logarithmic differentiation is enough to satisfy anybody, but because of time constraints, I need to show you 2 things. I need to show you that there's another very good example of logarithmic differentiation in the book on page 171. I'm trying to finish before Lady cuts me off. There's another good example on page 171, example 9. Look at it. And then here's your abbreviated homework assignment. And then if we have time and anybody wants to ask me a question about 72, you can. But the homework will be page 171, 1 through, what did I not get to talk about? 1 through 35. I wanted to do 69, but we didn't have time to do 70. So I'm just going to say 71 through 79. And that is just the odds. 1 through 35 is just find the derivative. You know what? I can make it even better than that. Let's say 1 through 21.
Your conference is scheduled to end in 2 minutes.
1 through 21, and then skip over to 27 to 35. That just cut out a couple yucky problems in the middle.
We still got 71 to 79.